All right, ladies and gentlemen, today's class recording is started. In all honesty, if you want, you can subscribe to the YouTube channel so that you get notified every time I upload something.
Gotta ring the bell button.
But yeah, so sure, ring the bell.
Comment on what awesome content you want to see.
Yeah, comment on what more awesome content you'd like to see. Like, you know, if you like what you see today, you know. All right. On Monday, we started talking about the quantum mechanical model of the atom. The quantum mechanical model of the atom really starts dealing with electrons. Okay? Protons and neutrons are in the nucleus. We know how many protons and neutrons are in the nucleus from the atomic number, from the mass number. We did all those calculations. In order to get a complete picture of the atom, a full model, we have to account for electrons. So, the first model that accounts for electrons is the Bohr model, which we talked about on Monday. All right. What are some features of the Bohr model? What are some important things to remember? Hannah, go ahead.
There are like rings around the...
Okay, there. Go ahead, keep going.
Where the electrons orbit.
Okay, there are rings around the nucleus where the electrons orbit. What do those rings tell us about those electrons?
They have a
Set path to travel on, what else? Set energy, and that's really the important idea. We call that idea of the location of the electrons relating to the energy that those electrons have, quantization. Okay? What do we know about the energy of electrons based on their location? Someone else out here? What does the location of the electrons tell us about the energy? How much they have? Go ahead. The ones closer to the nucleus have lower energy. The ones farther away from the nucleus have more energy. Good? What was the problem with the Bohr model? It only works for hydrogen. And hydrogen has how many electrons? One. So as soon as we got more protons and more electrons, it just didn't quite work. Okay? So, yesterday, you guys got introduced to two more scientists that I want you to be familiar with. One is this guy, Heisenberg, Werner Heisenberg. Okay? What did Heisenberg tell us about electrons? He came up with something that we now refer to today as the uncertainty principle. Zach, wait, Zach has his hand up. Okay, so go ahead, Zach. Sorry. Good. You can't know where something is and what it's doing at the same time. You can know one or the other, but you can't know both. Okay? It's like a mathematical impossibility. You don't really have to know why. It got into this weird thing with de Broglie and stuff like that. I won't hold you responsible for that. But the idea, Heisenberg's uncertainty principle says that we can't know the speed of an electron and its location at the same time. Okay? That then leads us into Erwin Schrödinger and his wave equation. Okay, so, Hannah, go ahead.
He said that the electrons were more in a cloud around the nucleus.
Okay, electrons are in a cloud around the nucleus. What does that cloud represent? Go ahead, Hannah.
Represent?
Yes. Got somebody else to take it?
Sure.
Elizabeth, what were you going to say?
No, I completely lost it.
Audrey, go ahead.
The most likely area of where the electrons are.
Good. Schrödinger's picture of the atom is based on probability. Okay? We can't know exactly where something is and exactly how fast it's going. But we can make a guess. Okay? So, this picture, which you have copies of this picture on the back side of the outline from yesterday. Okay? So, first, I have to interpret this picture for you a little bit better than I did in the video. I don't know if you guys noticed or not, but that video you guys were watching yesterday was 5 years old. It was from 2013. I think it was actually, if I remember correctly, it was actually 5 years to the day, right? November 6th. Okay? Which is weird, but, you know, apparently that was the last time I recorded class for this, for that lecture. Okay. So, these pictures that show up at the bottom bottom of this screen and also that are at the back of your outline. First, they don't represent electrons. Okay? That is way too many electrons, or way more electrons than any one atom has. Okay? That picture, and especially those dots, represent where electrons have been in the past. Okay? Remember we talked about you can know where something is or how fast it's going, but you can't know both. That is a picture that shows the location of electrons in the past. Okay? Let's say you had something that you wore, like a bracelet, or if you want to think of it like an ankle bracelet, like you were in jail or something, or on like house arrest. Okay? So, hopefully that never is the case, but you know. So, if that ankle bracelet sent a message to the police station to record your location every 30 seconds, okay? Well, you're under house arrest.
Like in this situation, it's a little creepy, but if I was...
You're under house arrest.
If I was criminal.
All right. If all of those locations were recorded on a map of Westlake with a dot, where would there be a lot of dots? At your house, school, Speedway, apparently, all right.
On the way.
So that path between, okay, so if the police were trying to find you, where would they look first?
Any place you go to a lot that's not your house.
Well, probably the first place they would look would be your house, right? So, there are places where you have been more in the past. Does that mean, so maybe let's say the police would go and try and find you at home, because you've been there a lot over the past whatever month, okay? Does that mean you will be at home? No. But it's a very likely location for you to be based on where you have been in the past. Okay? Is that good? So what Schrodinger is saying is that if we look at the location of where electrons have been previously, we can make a prediction about where they are currently or where they will be in the future. Does that mean that that's where the electrons will be? No. The possibility exists that you could be anywhere. Right? I think I said in the video. The possibility exists that you got up in the morning, stole a car, and you drove to Mexico. Okay? Right? You probably be driving pretty fast if you were already at Mexico and you left this morning. But is there a possibility that that's the case? Yes. Is it probable? No. Okay? What do we call these areas of high probability?
Probability density.
That's what it's based on. What do we call the area?
Maximum probability?
See those underneath headings? We call them, in general, we call them orbitals. Okay? So, Bohr's model is based on an orbit. What does Bohr's orbits say about electrons?
That they have a set path and also their energy level.
Good. They have a set path, and that relates to the energy that they have. They can be in this location, or this location, or this location, but nowhere in between. Okay? How is that different than an orbital? Good. There's no defined place, but what can we say? We can kind of predict it based on probability. All right. Are we good there?
Yeah.
Okay. So this picture that's at the bottom of your outline on the back side of the outline from yesterday is sort of like a timeline. Okay? The first picture that shows up is from Dalton and Dalton's atomic theory. What did Dalton say? This is your outline from yesterday. What did Dalton say about atoms? Go ahead.
If I'm not incorrect, it said that they are a solid sphere.
Why did, that's sort of what a picture of what Dalton thinks an atom would look like would be. What did Dalton say about atoms?
That they're indestructible.
They are indestructible. They are the smallest piece of matter that exists, and they are indestructible. That's why Dalton's picture of the atom would look like a solid sphere. There is nothing smaller than an atom, at least according to Dalton. Okay? But then J.J. Thomson came around. Which experiment did J.J. Thomson do? What experiment? The cathode ray tube experiment. What's the main conclusion that we get out of the cathode ray tube experiment?
Protons.
Nope.
Electrons.
Electrons, okay? So, electrons are a subatomic particle, smaller than the atom. That's why they show up as little pieces parts within the atom, okay? Then Rutherford comes along. Rutherford does, or his students, I guess, do what experiment? Gold foil. And the main conclusion of the gold foil experiment is the what?
Nucleus exists.
The nucleus, okay? So that's why we add the nucleus, that small part in the middle, okay? Then Bohr comes along. Bohr introduces the idea of energy levels, right? Orbits that electrons can exist in and nowhere else. That's why we have those rings. But if you look at Schrodinger's model, the one at the very, very bottom, right? What do you see about the area outside of the nucleus? Is it all green?
No.
Some of it is what?
Black.
Right? What do those black spots represent?
Places where there's not many electrons.
Black spots represent places where there...
There's a lot of electrons.
Hold on, wait. Hold on. Black spots represent what?
Electrons have been.
Where electrons have been in the past. So those are areas of what?
High electron
High electron density
density.
or high electron probability. What do we call those areas of high electron probability? Orbitals. Okay?
Okay, this is just a weird question. Why is clouds in quotations?
Because
Aren't they actually called electron clouds?
they are, but when we look at those electron clouds, there isn't one electron cloud. There are places around the nucleus where we are more likely to find electrons than other electrons, right? We call those clouds the orbitals.
Also, what's maximum probability? It was on the lab.
So, maximum probability. What was the most likely location where something was going to land? All right, let's grab out the outline from today. The outline that I gave you today. Let's get started on this. Okay. All right. So first, I'm going to save Roman numeral number 1 for tomorrow, so we can use that as a review of some of the things we talked about today. So we'll fill in Roman numeral number 1 tomorrow in class. Okay. But let's talk about Roman numeral number 2. Okay. What we find is that there are several orbitals that exist around the nucleus. Okay? There are several places around the nucleus where we are likely to find electrons. But they are all different from each other. So just like you have a house, the house is a likely place to find you. But your house has an address that distinguishes it from all of the other houses in Westlake. That's what we are trying, is what we will eventually end up with here using our quantum numbers. Each orbital each area of electron probability has a unique set of quantum numbers. Those quantum numbers distinguish that orbital from all the other orbitals. It's kind of like an address, right? We talk about this orbital being different from all the other orbitals. There has to be a way for us to tell that orbital apart from all the other orbitals that exist, okay? And so, we'll see here that each orbital has a unique set of 4 numbers. And those 4 numbers tell it apart from all the other orbitals. All right. Good for starters.
Fantastic.
Okay. Today and the beginning part of tomorrow, we're going to start drawing the picture, and then we'll go back and label the picture, or use the picture to define certain terms that we're going to fill the rest of the outline in. Okay? So, before you do anything else, here's what I'm going to show you. Okay? On the back of your outline, you'll see that there are 5 X, Y, Z axes, okay, or x's. So, you guys are probably familiar with an XY axis, right? X horizontal, Y vertical, yes? Okay. We use the XY axis to represent 2-dimensional space, a plane, right? Are we good with these terms? Okay. But one of the things that makes the next couple of days challenging is that we have to represent a 3-dimensional object, but we only have 2 dimensions to work with. Okay? So, the horizontal axis is always going to represent X. It's always going to represent the left, right. This up and down axis is going to be the Y axis. It represents up and down. This dotted line is a 3rd axis. We usually refer to that one as the Z axis. Okay? But you see that it's diagonal here, but it's also dotted because that 3rd axis doesn't actually go like this. It actually goes this way, okay? So we have something that we use to show left and right, something that we show to go, or we use to show up and down, and then something that we use to show front and back, okay? So this dotted line is not cutting, it's not breaking this picture in half. It's actually a 3rd line that comes out of the board and then goes like right into the board behind it. Are we okay with that? Elizabeth, go ahead.
And why did they draw it like
To kind of show some perspective, because I can't draw you a line that comes out of your paper, right? So it's just trying to show some perspective of a 3-dimensional object in 2 dimensions, okay? That's also why it's dotted, because it's not really there. It's just kind of trying to show us like a tilted view of it or something, okay? All right, so the nucleus of our atom is always going to be at the origin of that picture, okay? So you'll notice that in my picture, I put a little black dot at the origin, okay? Before you draw anything today, okay, I want to show you this, okay? This picture, this is where we're going eventually, okay? You will see, hopefully in a little while, that there is a pattern that follows, okay? You'll see that there's lots of colors and lots of overlapping, all right? But right in the middle is the nucleus, okay? I'm not doing this to scare you. I'm doing this because I want you, when we start drawing some things, to make sure that you're not drawing things too big to begin with so that you can't fit everything, okay? Eventually, the top one, the top axis that's on the top back side of your outline that I gave you today is going to look something like this, okay? All right, so we are going to start drawing orbitals, areas of high probability of finding electrons. If I say ground state, does that mean anything from our discussion the other day? If I talk about the ground state of an electron, does that mean anything?
it's not
We use gravitational energy to sort of like come up with an example of it, but let me show you this, right? No, not that. Here and here, okay? So this bottom rung of the ladder was labeled as ground state, okay? From an energy perspective, what does that mean? Let's go with little energy, right? Ground state is the lowest energy that something can be in, right? Remember we kind of talked about the idea that if something has a high energy, it wants to try and get rid of it and go to a low energy, okay? Ground state is the lowest energy that something can be in. So, going back to this picture, where is the most likely spot for us to find an electron on this three-dimensional drawing? Well, what do you know about electrons?
They are attracted to protons.
They are attracted to protons, right? Where are the protons in this picture?
The very middle.
They're in the very middle. So where are we most likely to find electrons? Pretty close to the middle, okay? So, first thing, you'll notice I'm using colors and shapes, okay? You're going to use these colors and shapes to help represent stuff. The first orbital that I want you to draw looks like this, okay? Notice, before you actually draw it, okay? Let's talk about this orbital a little bit. What can you tell me about this orbital? The orbital represents locations of electrons, right? So, Kate, where is it in relation to the nucleus? Close to the nucleus, okay? How big is it? Not very big, okay? What shape is it? Is it actually a circle? It's actually a sphere, right? Because we got to talk about it in 3 dimensions, okay? So, the first orbital that we draw is a small spherical orbital close to the nucleus, okay? Oh, you can, yeah, you can color it in if you like, that's fine. Good. So, this is your drawing, so, you know, you'll see after a while that there's a pattern that develops here, and that will help you when you're drawing later things. All right, good with this? Okay. Small, close to the nucleus, spherical. What's true about the energy of the electrons that would be in this orbital? It would be a low energy state, okay? Now, will we find a lot of electrons in this space?
Yes.
Do electrons want to be there?
Yes,
Yeah.
it's closest to the nucleus.
Yes, because it's close to the nucleus. And negative electrons are attracted to the positive nucleus. But if we put too many electrons in that space, what starts happening? They start repelling each other. So, last point for today. Hold on. Last point for today. This drawing, moving forward, is a combination of 2 things. Okay? Electrons are one. Hold on a second. I know what time it is. This drawing is governed by 2 things. 1, electrons are trying to get as close to the nucleus as they can, but 2, trying to stay away from other electrons as best as they can. Okay? So those 2 ideas are basically going to govern the rest of the things that we're going to draw in this picture moving forward. How close can electrons get to the nucleus while still being away from other electrons? All right? Okay. Oh, one thing. There's not a lot about this in the book. So pay attention in class, ask questions, and we'll move forward with it, okay?